Heather?
A sample of 4 mixed gases is at 716 something. The particle pressure, partial pressure of gases A and B are shown, and gases C and D have equal partial pressures. What is the partial pressure of gas C? And I said C.
C is correct. And number 3. Go with Hannah.
A sample of 3 mixed gases is at 632 grams. If the partial pressure of CO2 is 124.3 and the partial pressure of N2 is 46.1, no, 461.9, what is the particle pressure of O2? And I said B, 45.8.
B is correct. So, Colin, right now, these are the quiz questions for tomorrow.
I'm fine.
So I'm glad
So that's like right here,
yeah, you're gonna want to check yourself on this so that you know what the answers are, so that you don't get a low grade and then get less keys money. Who's got the number 4? Sophia.
Which is an intermolecular force after it's C?
Number 4 is C. Number 5, Hannah.
Of the force listed, what is the strongest? And I said covalent.
A is correct. Number 6, Hannah.
Which is the characteristic that increases the substance? Viscosity. I said
Viscosity.
viscosity. And I said A, larger particle size.
6 is A. Number 7, Hannah.
Which is defined the combination of pressure and temperature that all states of matter can coexist in equilibrium. And I said B, triple point.
7 is B. And Heather.
The average speed of oxygen molecules in the air is about, and I said C, 17 kilometers.
That is correct.
Okay, 12.
Uh,
Oh, okay. So now I'm sorry.
Oh, sorry, I didn't go. I went to number 12 instead of 8.
12 is C. Number 8 is C. I think we're on number 9, right?
Yeah.
Number 9, go ahead.
Oh, I didn't get number
Am I get 9? Okay, so number 9, it says a sample of 3 gases is at atmospheric pressure, and the partial pressure of gas X, gas Y are shown. What is the partial pressure of gas Z? So you basically have to subtract Z, right? So if you got your total pressure, right, that should have a total there for you. So your answer is number 9 is A. All right, number 10. I got 10. All right, so number 10 says samples of helium and sulfur dioxide are released at the same time into opposite ends of a long tube. Which position shows the location where these 2 gases will collide? And they're saying D is correct. They're saying D because SO2 is obviously larger. All right, number 11. We got 11. 11, in the kinetic theory, the particles in a gas. You should have been able to look that one up. Move independently of each other. And then we've already done 12, so we're on 13. We got 13? Okay, it says, which of the following statements is true according to the kinetic theory? So 13 is C. Particles of a gas collide with each other and with other objects. I got 14, Hannah.
particle in a gas is
Phase diagram. No, that would be freezing, and ice floats, so water's more dense as a liquid than as a solid.
30.
at room temperature.
Now you're close. Water's kind of like a pyramid. It goes from the most dense at this temperature, and then it decreases its density as both a liquid and then to a gas and to a solid. So it's kind of like
75.
decreases as a solid, decreases as a liquid to a gas. The temperature is around 4 degrees Celsius.
Which is what?
It's pretty close to freezing. 0 degrees Celsius is freezing. So 4 degrees, 25 degrees Celsius is room temperature. So 4 degrees Celsius, you would need to have a jacket on. It's not freezing, but it's going to be close to it. So what temperature is salt water most dense?
What's the ocean state?
Do I know what temperature salt water is most dense? It's right at its freezing point. So at the freezing point of salt water is when it's the most dense. And when salt water freezes, does all the salt leave the water? No, it does not. So you can't like melt sea ice and drink it. It's still too salty. So you got to be aware of that. You have to go to like the top of the iceberg where it snowed or rained and produced ice. Take some of that, and you're good to go.
What if you just heat it up? If you boil it.
No, boiling it will not get rid of the salt. The salt is still stuck in the water. You'd have to distill it. Good question. Diagram 438. They say, under what conditions is diamond most likely to form? And then you say, okay, at these pressures and at these temperatures.
100 pascals.
So you're going to have to be above 10 to the third, or close to 10 to the fourth there, for it to occur. That is, the pressure is going to need to be 10 to the fourth there, close to it. It looks like 1, 2, 3, 4. Starting point, the triple point, and you take your measurements from there as far as under what conditions is diamond most likely to form, and the answer is C. Alright, so let's move on into the next chapter. The temperature at which the motion of particles theoretically ceases is what?
0 Kelvin.
Right, 0 Kelvin. So they're saying that the motion is going to theoretically cease at 0 K. Now it doesn't do that. That's the point where all substances are solids. That was what was theoretically predicted. So if you're doing an experiment like we do at the science fair, you predict what's going to happen, and then you just kind of make your results, and then you talk to people about your results if they don't happen, which you theoretically predicted. But you can look at the page 445, and it shows you why they're theoretically predicting this. Because you have 0 right here, and that's volume. 0 volume means that you don't have anything there. Right? 0 volume, like 0 water in the container. So if there's 0 volume, they're predicting that the motion is going to cease.
0 light.
Everybody understand that?
Let me read myself. Of galaxies. The regal regularity of diamonds, the completely compelling
Is it
complexity of life, the murky mysteries of chemistry explain this part.
Yeah, so it's also unlikely, it states, and then it says here at the bottom, Garrett, it says here at the bottom, the reassuring theme of this chapter is the universe gets less improbable all the time. So the improbability is associated with trying to figure out if you're talking with a linear timeline. This is really about justifying a linear timeline. Like when you go into your history class and they have like the history of the presidents, that's a linear timeline. So what they're doing here, they're trying to justify that with the formation of matter at one specific time, and then from that you have like a timeline. Because in order to have a beginning to time, you must have matter created from nothing at a specific point. Because that gives you a beginning to time. Now, up here on the overhead, what they're doing now, they are introducing emptiness. Because the temperatures in the textbook are not getting us to where we can turn something into nothing. So the thinking is that emptiness is seen as capable of producing colder temperatures, because emptiness is the absence of nothing. So the absence of nothing would be the absence of empty space. So the thinking is that if you have the absence of this, that's going to be a colder temperature. That's the thinking. Now, they have not been able to produce emptiness in a lab. It's just this theoretical, hypothetical idea.
The book said that if you have a vacuum, there's no matter in it at all. So
That's nothing. Nothing would be the absence of what you just said. That would be emptiness is the absence of what you just said.
AKA space.
So you're taking away even space.
oh, okay.
So you've removed everything. Emptiness is the absence of everything. Their thinking is that that would be a tool necessary to drive something into nothing. The colder temperatures would do that. Because if you look right now, they have these particle accelerators. They're cooling matter and they're smashing it. But when you smash it, all you're doing is then, yeah, you're making it hot again. You're just causing it to move a little bit more. You're seeing, you know, things that are creating at that level, but you're not really driving the temperature down like you're seeing in this diagram and the one I gave you on the back side of the sheet when you came in, where you have zero volume. Temperature is the only way we know how to drive down a substance to where its volume is decreasing. And when you have zero volume, that's the definition of empty space, or nothing. Nothing would be the definition of zero volume. Emptiness is the definition of the absence of empty space, or the absence of space. That's the definition of emptiness. It's the absence of space. Because you have space right here, right? And you have something in the space, but emptiness is the absence of both of those things. You don't have space and you don't have something. Right. The absence of everything would be emptiness. You have to look at the big picture. Any process that concentrates matter and or energy in a system is more than offset by a greater amount of spreading out elsewhere in the universe. The overall effect in the universe as a whole is to spread things out. Now, where does the Big Bang say that it happened? Hannah, where does the Big Bang say that it happened? Where? Chris? No, but where specifically? Where does the Big Bang say it happened? Garrett, where does the Big Bang say it happened?
Okay, the Big Bang says that at one point there was a big bang and it started everything
Where?
Where does it happen?
Where?
in nothingness.
No, where specifically in the universe?
The middle.
The middle.
No, it's basically, it says it happened everywhere at once.
See, I was right.
Yeah, so here's the situation. If it happened everywhere at once, and you're saying matter is constantly spreading out, you have a very difficult time dealing with an origin. Where's your origin to measure where things have spread out from? If they're spreading out from everywhere at one origin, it's easily to determine where your starting point is. You understand when you do reference points, you try to get where your starting point is, but your starting point is everywhere. You're going to have a hard time justifying that it's been moving, I guess you would say, away from a place, because it seems to be moving away from everywhere, right? It's kind of confusing when you look at it that way. If that's the conclusion they're making, that it happened everywhere at once, right? It seems very probable you could replicate that in a lab as far as create emptiness to
Good morning.
make something and thus validate the steady state theory.
Acids and bases affect a yeah, and how buffers are made by combining weak acids and so. What is it?
Carlos, can you read it for us?
The temperature at which the motion of particles theoretically ceases is C.
Yeah, so the temperature at which motion theoretically ceases is what temperature? Yeah, absolute zero or 0 Kelvin. So they're saying theoretically that matter or energy should stop moving. Now, if energy stops moving, what is it not doing? It's not working. Right? So if it's not working, it's not energy, and if it's not energy, it's not a force. And if it's not a force, it's not technically going to be matter, because force equals mass times acceleration. So if you stop moving, you're not going to be matter or energy. Motion is associated with energy, and matter is associated with force. Is everybody clear? That's the theoretical. It doesn't do that. It still oscillates above freezing, probably about 0.4, 0.5. And where is water most dense? Anybody know what temperature water is most dense? Around 4 degrees Celsius. Ice is less dense than liquid water. So water is most dense around 4 degrees Celsius. Now this is important when we turn the page over to 438 and you see, now question number 6, it says, under what conditions is diamond most likely to form? People care about diamonds because you can make them synthetically. I purchased some synthetic diamonds that are real diamonds for my wife, earrings, 1 carat, and they cost about $150 for 1 carat. If I were to go out and buy a 1 carat diamond that has a good color and clarity, you're talking around $5,000. So I was able to buy that for $150. And I would just rather prefer to do that with earrings than to spend $10,000 on some diamonds that are like natural. So I bought my wife real diamonds, but they were synthetically made, but they're still diamonds. In order to do that, you have to understand what temperatures you can make a diamond. So here, the triple point, where you have the graphite liquid diamond, is where it says under what conditions is diamond most likely to form. That's the triple point. So you're going from this point where you see diamond, liquid, and graphite right here, and that's the letter C, the pressure of 3,500, the pressure of 10 to the 5 atmospheres, less than that, and then less than 3,500 Kelvin, and then greater than atmospheres of 10 to the 5th K. So here you see 10 to the 5th. If you go right over, you're seeing 10 to the 5th there. All right, likely, right? So where does the Big Bang say that the formation of matter happened? Anybody know? Where? Does anybody know specifically where? Well, the thinking is that it happened everywhere at once, right? And going back to question 18, 18 says that absolute zero is the temperature, theoretically, at which motion should cease. And we talked about that if motion ceases, then there would be no work, because work equals force times distance. And then there would be no force, because motion wouldn't be moving if it ceased. And there would be no mass, because force equals mass times acceleration. Now up here on the board, right, I'm pointing out to you that the reason why they bring up emptiness in the Big Bang is because the temperatures are not cold enough, according to our data, to turn something into where it freezes and there's no more motion. So this diagram that you see here in the book, where they're showing you a volume of gas and they're taking it to absolute zero, if you were to take it there and it stopped moving, then it would cease to exist, and it doesn't do that. What exists at absolute zero? What type of substance exists at absolute zero? Talked about yesterday. Starts with the S. Solid. Like if you take any substance to absolute zero, it's a solid. Like helium is an example of that. So you take it to absolute zero, and you have a solid there. So when we look at our universe, right, there's an incredible amount of evidence supporting that matter has always been in existence. Because emptiness is theoretical. Emptiness is the absence of space. Like here's space right here, and then there's some matter like gases moving around in it, but the majority of the room is just what you're going to call space. Now, empty space is the absence of space and matter. Emptiness is the absence of both of those things. So their thinking is that that would be capable of having a cold enough temperature to stop something from moving. That's the thought. But if you go to 0 Kelvin, you should have just space. If you go out into outer space, the temperature is around 4 Kelvin. So outer space is fairly cold, very little movement's happening there, just because you have more space than you have matter. At 4 Kelvin, that's what it's telling you. So the closer you get to 0 Kelvin, and you were to, like if you were to move all the gases out of a container and drop it to 0 Kelvin, you would still probably have some matter in there, but it would be very little. So if you've got, the absence of movement in space, the absence of mass in space would be the definition of nothing. Is that right clear? No movement, no mass in a space would be nothing. You just have space. Space, right? That would be space. And then emptiness says there's no space, there's no mass. That's the absence. That's what emptiness means. It's the absence of both space and matter. So what's there? Emptiness. And that is considered to be what's going to drive the temperature down. But that's a theoretical. We've never been able to eliminate space. Right? We've never been able to do that. So there's just this enormous amount of evidence supporting that matter has always been. It's almost comical in a way to think that it hasn't been, because there's no evidence anywhere to support it. The evidence would be a steady state theory if you could turn something into nothing. But we've never been able to do that. But all these people are supporting an event where you have nothing and then something, or beginning to time. And the reason, why do people so much want to support a beginning to time? Does anybody know? Why do people want to support something that's never been proven? And the evidence is stacked totally against it. It's what it's saying right here. It's saying it's so unlikely. It's unlikely because the evidence is stacked so against it. So why are people so in support of a beginning to time? Anybody know? Huh? No, it doesn't necessarily say that. I mean, religion says, like, in the beginning. It doesn't necessarily say before time. It just says in the beginning. People like to say a beginning to time because it creates a linear timeline. A linear timeline, like if you go into history class, you got your little linear timeline, bam, 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 bam. That's what people like to document things like, I have done this at this time, I get credit for it, so I get the royalties. So it allows you to own property and so forth. A linear timeline allows that more so than if you don't have a linear timeline, it's a little more difficult to say who owns what. Do you understand? Without a linear timeline, you could argue that, like, the Indians were here first, right? And you could argue that they weren't here first without a linear timeline. Does that make sense? All right, so